right. Thank you very much, Sasha, for the invitation to participate in this seminar. I think it's a really great idea and, of course, a very interesting topic. So what I'm going to talk about is some work we've been doing in the East African Rift that really started in 2005 when Bernard Marty and his colleagues invited me to start working on Oldonyo Lengai. And since then, our ideas have evolved somewhat. So I'm going to present a summary of our current thinking. A lot of this is still in the kind of hypothesis stage, and I'm very curious to hear what people are thinking. So let's see. Just to set the stage here, the East African Rift, of course, is a major rift in the world. That's where continental breakup happens. It has two branches. But what I want to focus on are the carbon emitters from this rift. And for example, there's a major carbon emitter, Nyiragongo Nyiramuragira, which is an active volcano in the Congo. And then there is Oldonyo Lengai, which is the only currently active carbonatite volcano. Both emit significant amount of carbon to the atmosphere. And we have quantified, or others have quantified, the carbon output, or the CO2 output of Nyiragongo in different ways. But just to give you an idea, it's about 4 megatons of CO2 per year. And that is quite significant. I think Etna is about 3 megatons or 3 to 4 megatons. Kilauea is 1 megaton per year. And mid-ocean ridge basalt total is about 50 megatons, 60 megatons per year. So it's a significant amount of carbon that's being emitted from Nyiragongo to the atmosphere over a long period of time, like 30 years or more. And what we can calculate very easily what the source of the carbon is, or how much carbon there is in the source. And you can simply take a magma flux and a undegassed magmatic CO2 content, and you can make this very simple plot that, of course, if you have higher magma flux, you require less CO2 in the undegassed magma. If your magma flux is high or low, then the CO2 content of that magma has to be higher in order to satisfy those 4 megatons per year. So what is the magma flux at Nyiragongo? Well, there's only one study. It's poorly constrained, but it places it about here at about 0.3 cubic kilometers per year. So that would put it at about 4,000 parts per million of CO2 in the undegassed magma below Nyiragongo, Nyiramuragira to supply that CO2 flux. And calculations like that are very straightforward. And of course, there are some caveats. But Anderson in Poland in 2017 did a much more sophisticated approach to model the magma supply of Kilauea volcano to sustain the CO2 flux from Kilauea. And by the way, Kilauea is erupting right now, so this is a very timely comparison. But the undegassed magmatic CO2 content under Kilauea, they calculate about 1 weight%. And Nyiramuragira is over here. So Nyiramuragira is a bit lower, but you have about 1 weight% of CO2 in the source. And that means that the magma at Kilauea becomes saturated and degasses CO2 at about 30 to 40 kilometers, right? So that's the CO2 content in the magma. Then you can calculate the carbon concentration if you just assume 10% of melt and you just convert weight% to mole% or ppm, and you get Nyiramuragira being here. This is Kilauea over here. Oldonyo Lengai, we estimated early on at about 300 parts per million, perhaps. So this is a maximum estimate. But the point is, everything is a little bit higher than MORP, mid-ocean ridge basalts. The most recent estimates of mid-ocean ridge basalts about 37 plus minus 14 parts per million. So this is an illustration of how we can estimate carbon contents of the undegassed magma, or therefore also the undegassed mantle that is supplying the CO2 to these volcanoes. And it shows that the CO2 content in that source could potentially be pretty high. Now, Raphael, I think will talk much more about the Afar, but a lot of the degassing in the East African Rift happens through diffuse degassing. And a lot of that diffuse degassing is focused around faults or around areas close to volcanoes. So we have talked a little bit about Nyiragongo and Oldonyilengai just to illustrate this. And Raphael will talk about the Afar further north. Now what I want to talk about is some of our thoughts. Where does this carbon, this extra carbon, come from? And that's where the craton plays an important role. So when you, maybe I can, oh yeah, I can go back. So here's the Tanzania Craton. You're probably familiar with this, but it's an old mass of rock that's been sitting there for billions of years, and the rift bifurcates around that craton. So when you investigate the gases and gas fluxes that are in the transition between the active rift, which is the Natron Basin, the Magadi Basin, and Oldonyilengai sitting right here, and then the Craton, which starts really at the Manyara Basin and the Balangida Basin, which is right on the Craton. You see, of course, very dramatic differences, right? And this is to be expected from a gas geochemist's point of view. This is nothing that was a big surprise when we did this study. So in Natron and Magadi, the CO2 flux is high, 30 to 70 grams per meter square per day. And you can argue how much of that is mantle, but it's dominantly mantle, I would argue. But when you go over to the Craton, the CO2 flux just drops down by an order of magnitude, right? There's no CO2 coming out of it. And so that's interesting, right? And is to be expected. Now, when we look at the helium isotopes, again, what we see is that in the rift area, we have relatively high helium-3,4 ratios, which implies a mantle-derived contribution or subcontinental lithospheric mantle-derived contribution with values as high as about 5 to 7. And again, the contrast is striking when you go onto the Craton. So the Craton has these very low helium-3,4 ratios that are really typical crustal helium ratios, isotope ratios, indicating that there's no mantle helium coming through it. So the springs, and that is an interesting finding, I think, is a very, very different between the mantle area in the rift and the Craton area. We see that in the rift area, the CO2 nitrogen ratio is very high and the CO2 helium ratio is very, very high. And on the Craton, the gases are very different. They are dominated by nitrogen and helium. And so these gases that are bubbling out from the springs or are dissolved in the water from these springs have up to 1, 2, 3% helium. And the rest of it is essentially nitrogen. There's no CO2, there's a little bit of methane sometimes. So the gas composition between those two areas is dramatically different. CO2 poor, crustal, nitrogen rich, helium rich. And when you look at the geophysics, we see that the Craton boundary is right here, exactly where we did our transect. So again, this is an important boundary where the Craton meets the adjacent mantle, and we see the CO2 flux is very low. It jumps up. Once you get into the mantle area, the helium-3,4 ratio is high and remains high. And so Oldonyilengai, in fact, sits right here at that boundary where the CO2 starts to, is really peaking, where you have the most mantle-derived helium isotopes, and where you also have mantle-derived carbon isotopes. Now, the CO2, the source of the CO2 we have thought about, where does the CO2 come from? And our idea of working with Steve Foley was that over time, this carbon accumulates underneath the craton and gets stored underneath the craton for billions of years. And the source of that carbon is ultimately plumes, so the kind of type of carbon that I described at Nyiragongo, near Muajira, which might be perhaps plume related. Although there's some controversy, there's no high helium 3-4 ratios. So, but I didn't go into the details, but there's obviously evidence in East Africa for large super plumes. So plumes contribute to the CO2 that is stored at the bottom of the lithosphere and accumulates there over time. And in fact, I was at GU 2019, and Gibson and McKenzie used a completely different model to also calculate the accumulation of carbon underneath these cratons. And so,
Tobias, this is 10 minutes over.
10 minutes. Okay, so what we think is that because you are adding all this very light carbon over time, the craton or the crust is able to break apart, and that is because you have low density material underneath the craton, and then that low density material moves to the side as the craton is splitting apart, and you essentially get this this image where you have solid carbon that has been accumulating over time and is migrating then to the area underneath the rift. And due to that carbon addition to the mantle or to the asthenosphere, you start to melt that region, and you get melting and formation of magma chambers, high CO2 degassing, whereas on the craton, you simply do not access any of that carbon, and you get low CO2 emissions and very crustal gases. So that is the quick summary of 15 years of work or so. Thank you.
That was much quicker than I expected. So there's a lot of time for questions. So we have the first question. David, can you unmute yourself and ask the question yourself? That makes things more exciting, I think. David?
Yes, can you hear me?
Yep.
Yeah, so Tobias, thank you for your presentation. I'm very interested about this carbon dioxide topic, and I wanted to ask you, I mean, some of this carbon dioxide comes to the surface, but is it possible that some of carbon dioxide stays in geologic reservoirs? And there is, if yes, is there a way to model or to estimate the quantities?
I think that if you have the right structures in the geology, you could potentially accumulate some of that CO2. And we see that, for example, in the Rio Grande Rift here in New Mexico, just north of Albuquerque, where we have the Bravo Dome and those structures that have accumulated carbon and as well as helium in underneath an impermeable cap. And that the source of that CO2 is essentially mantle or volcanic derived. So you would have to have the right structures to do that. And we haven't looked for those things, but there's evidence for helium reservoirs on the craton. And again, we don't know the subsurface structure, but I would think, yeah, it's possible.
Thank you very much.
Okay, next one is Simona.
Actually, it's not Simona, it's me, Thomas Wiersberg. I'm sitting here together with Simona. Tobias, very nice talk. Thank you very much. You mentioned that there is no evidence for mantle helium at the cratonic gases, but my question is that just be the case because it's simply swamped by radiogenic helium, because cratonic gases are generally enriched, very much enriched in helium-4 from crustal processes. Maybe they are there, you just can't see them. Could that be the case?
It could be the case. However, the ratios are really very, very low, 0.04, 0.02. And those are ratios that, you know, Raphael can talk more about this, but those are ratios that are found on really old cratonic shields, right? Like Canadian shield or so on. And so it could be, but it would have to be very, very seriously diluted. Somebody, of course, can model this. But yeah, they're very, very typical of crustal, very, very crustal gases.
Okay. Now, in fact, just to comment on this, I made some measurements on my PhD thesis on lamproids and kimberlites, so mantle rocks, and also did some noble gas studies. And there was absolutely no evidence for any mantle helium because the samples were more than 1 billion years old. So it was simply swamped by that radiogenic isotopes.
Oh, okay, yeah. Yeah, I mean, the helium production in the cratonic crust is an interesting topic, and that production can be calculated, and so you could figure out that helium would also produce hydrogen, and that hydrogen would be converted to methane likely in the crust. We don't see any hydrogen at the surface, very little, but we do see methane in some places. So it's an interesting question.
Okay, thanks. Maybe Thomas, we can put a link into the chat, and then we can check on what you were mentioning before. Karen.
Hi, Tobias. Thanks for the talk. I was wondering if you could comment on how this would apply in the Rungwe volcanic province, essentially on the other side of the craton.
Yeah, so the Rungwe volcanic province is right where the craton edge is meeting the two rifts, essentially. And there we find pretty high 3-4 ratios and magmatic CO2. So the ratios there are 6 Ra and clearly magmatic CO2. So on that side, again, we are back into the rift, right? So that's the other edge of the rift, and it's clearly showing us non-cratonic but magmatic or mantle-derived gases.
Thank you.
Okay, Lee-Ann, you're next.
Hi, Tobias. Thank you. This is such interesting work. I apologize if my question is a little vague. I'm still thinking it through myself, but I was intrigued by your last slide, and you're showing how the CO2 migrates laterally to the edges of the craton and affects the partial melting process in the mantle. And I was wondering if you see this as a continuous migration that just sort of ultimately leads to the process, or whether there's some feedback among the migration, partial melting, and the tectonics of the rifting so that the process sort of accelerates or is a positive feedback.
We haven't modeled this, in any detail. It is my inclination that I think it's a continuous process with feedback, and the physical model that I presented from Jolante van Wyk is simply taking the density difference and letting that sit over time, not doing anything to stretch the continent, not implying any kind of mantle movement or convection, just simply letting it sit, and over time that lighter material will migrate to the right in that case. And of course, once that starts happening, and if you have some tectonic forces that obviously are occurring in the region, then I would expect there to be a feedback mechanism, right? So I agree with you that it probably is a feedback mechanism.